Welcome back, ladies and gentlemen. I hope you're having a wonderful afternoon. This is the third episode of From Atoms to Axons with
Ibrahim Shahrur
and Bilal Hamoud. Today we have a special surprise for everybody. Today is a special day. Wouldn't you say, Abe?
Oh wait, I hear something.
What's that noise?
Sounds like a drum roll.
A drum roll? That must mean today's the day.
It is the day.
The day.
Today is the day of the Nobel Prize in Physics.
Oh my God. I'm so excited. Abe, please, I can't wait any longer. Tell me who won.
Well, we got 3 winners today, and they were actually all in the fields of biophysics and sort of atomic, molecular, and optics. It's pretty interesting. One person got the Nobel Prize for optical tweezers.
Optical tweezers? What is that?
Great question. So I had to do my reading before this because I had no idea what optical tweezers were.
I just assumed it's like tweezers for your eyelashes.
Yes, that's what they are.
Man,
they deserve a Nobel Prize for that.
That's crazy.
But no, optical tweezers happen to be these very precisely engineered tools where you can actually lift or levitate very small objects, certain biological objects if you want, using exactly what the word says, using light.
Light itself is lifting these on a microscopic scale.
Exactly. This is very useful for biologists, for biophysicists, for chemists, and this is why it deserves the Nobel Prize.
Are you kidding? Of course. Now we can finally play the world's smallest violin.
You can actually manipulate a lot of molecules and biological proteins and stuff like that. So that's why this was worthy. And then the other Nobel Prize was given for these ultra-fast light pulses of high intensity. So usually you could have ultra-fast laser pulses of low intensity. Mm-hmm. But these two physicists, Donna and I believe Giorgio, they discovered this method of having high-intensity, short-time pulses, which is also very useful in the fields of biophysics.
Huh. So now remind me, who are the 3 winners?
So the winners happen to be, I believe one of them...
I believe one is Arthur Ashkin, and the other is Gerard Moreau. Now, the third, and actually is why today is such a special day, is Donna Strickland. Now, Donna Strickland is the first woman to win the Nobel Prize in Physics in the past 55 years.
Wow, that's a lot.
Yeah, it's crazy.
Tells you a lot about the status of physics and how the STEM fields, or particularly physics, are not very populated or have troubles with...
Yeah, I understand what you're saying. It's nice to see that it's kind of coming around to an era where no matter who you are, you can get involved in the field and
right, and
be well renowned for it.
Exactly.
So now I'm excited. Abe, today we have a special topic.
It's one of my favorites.
But on the topic of Nobel Prize, I want to know, because before we dive into our topic, what is our topic again?
Today we're going to be talking about the Fermi paradox.
The Fermi paradox, and that is a juicy topic. But before we dive right in, I want to ask, what does Wayne State have to do with any of these Nobel Prize winners?
I'm glad you asked, because Wayne State has this tradition of hosting the Vaden-Miles lecture. And it's hosted by the physics department. And for the past, I believe, 3 years or more, they have been hosting... they've been calling in for Nobel Prize winners to give lectures. We had Kip Thorne give a lecture. Yes.
Kip Thorne.
The Kip Thorne, the physicist who helped Interstellar
Black hole theory?
Black holes and the animations, the way black holes moved, because it involved a lot of this geometrodynamics, which is how space itself would react and move when there is energy and mass around it.
Oh, kind of like that song by Dead or Alive, "You Spin Me Right Round," right?
Yeah, exactly. They also had Adam Rees, who was a cosmologist, an experimental cosmologist, and he was part of the team that discovered the accelerated expansion of the universe. Now, the Nobel Prize was awarded to Adam Rees in 2011, but before that, they had discovered, back in, I believe, 1998 or something, that the galaxies, wherever they look, the galaxies are actually moving faster and faster away from us. And so they concluded that the universe is expanding at a faster rate. And then one more Nobel laureate was the lecture we went to.
So for those of you who are not familiar, Abe and I, one of our first experiences outside of the university, I guess outside of a classroom setting, was during this Nobel candidate, or Nobel laureate, who had come in to give a lecture. And I cannot begin to describe, what was his name?
His name was Michael Kosterlitz.
Michael Kosterlitz had the least bit interest in physics out of anyone I've ever met. Out of a regular person, he just didn't care for physics.
What was his passion?
He loved to rock climb. Absolutely loved it. And so his entire, I want to say like half of what he spoke about was rock climbing. He gave this giant presentation on topical excitations in 2 dimensions, some topic that, if it didn't sound dry, was presented in a manner that would make Thanksgiving turkeys jealous. It was so absolutely dry that he just skipped through the slides, didn't very care much for his own work, but when he got onto the topic,
that's when he got excited
of rock climbing. He got so excited. And so I've got to say he's my favorite of the Nobel Prize winners in physics.
We took pictures with him, and then you talked with him about rock climbing.
We spent the entire time talking about his time in Italy, climbing the rocks, how he has a rock named after him over there because of how difficult it was to climb. I found it absolutely fascinating. Now, physics, the Nobel Prize winner in physics, we're hoping that Wayne State brings them around again this year. We'd love to have Donna or Gerard or Arthur, any of them, come on in and talk about these electric tweezers. Or not electric tweezers.
Optical tweezers.
Optical tweezers, which sounds super, super interesting. Really getting rid of those micro hairs that you have.
That's their use.
Yep.
That's why they deserve the Nobel Prize.
So, Abe, I think I'm ready.
Let's just dive into this.
So first we should define, what is the Fermi paradox? Because I'm not quite clear, Abe. Please, indulge me.
So the Fermi paradox has to do with the existence of intelligent life outside of Earth. Now, one could ask the question, is there intelligent life on Earth?
Wow.
But assuming so, is there intelligent life outside of Earth? And so Enrico Fermi was sort of pondering this question. He was thinking, okay, look, there's a lot of galaxies out there, right?
There are millions.
Millions,
At
perhaps billions.
Billions.
But here's the thing. Let's
With
just
a B.
only, with a B, let's focus on the Milky Way. Let's not look too far. If we just look at the Milky Way and we count how many stars there are, then we get a number that's about 100 billion. Okay?
100 billion possible
stars with planets, exactly, with a B.
That could survive.
Right. So we think that with every star there is at least one planet who resides in the habitable zone.
So not too hot, not too cold. The Goldilocks zone, as
exactly,
they would
the
call it.
Goldilocks zone, such that life could evolve. And here's the problem. Given this vast number of planets that are habitable,
we would have expected a civilization to have grown and colonized the rest of the galaxy.
Exactly. We should see the aliens, but we don't.
I see them all the time on the History Channel.
Those are special types of aliens.
Ah.
Actually, that's a good idea. We solved it. The show's over.
Oh, well, thanks for having us, guys. This is going to be From Atoms to Axons, episode 3, ending out early.
But if we disregard those aliens and we look at what we actually mean by aliens, we don't find them. And that's the paradox. So much possibility, yet nothing.
So why is this a thing? Why don't we have life outside of Earth, intelligent life outside of Earth that is developed?
So there has been many proposed solutions, and so far there is no consensus about what's the right solution.
It is a paradox, after all.
It's a paradox, but usually paradoxes?
Paradigms?
Paradoxin? Let's Google that. So usually paradoxes have a solution after a while. Say Zeno's paradox. It took calculus to solve that one. But usually in general, we could find a solution to a paradox. In this case, we still don't have one. And scientists are looking for a solution, but there are a couple of, or maybe more, a few candidate solutions out there.
Mm-hmm. To these paradoxes.
Right, especially this one, the Fermi paradox. And yes, I was right, it was paradoxes.
Mm-hmm.
The first solution deals with sort of barriers of civilizations and
so kind of
advancement.
So kind of like the barriers of entry into a field or something. You need to meet these basic requirements.
Exactly. So with a barrier, usually you want to cross it. Otherwise, that would be bad news. And what are some types of barriers that we're talking about? Well, it could be something like climate change, right? So you have this life that evolves on a certain planet, and then they reach a certain level of intelligence, but before they get to leave the planet and conquer the galaxy, they hit a wall in that the climate changes too fast, and they go extinct. That might be happening to us.
So a barrier that prevents the advancement of the civilization because of its environment.
Exactly.
Okay, so that's one possible solution is environmental effects.
Exactly.
Now, what about the technological barriers?
Some people have proposed, I think it was Nick Bostrom, he was proposing that the reason we don't see alien life or intelligent life is because they reach a certain point of advancement that they actually cause themselves to go extinct, either by nuclear war or some sort of feud between them, and then they basically wipe each other.
So politics is another barrier where politics basically gets in the way of a civilization's advancement to the point where they become extinct.
Exactly. Politics with the technology, with the really advanced technology. Another possible barrier could be biological. For example, it could be disease. It could be some sort of microorganisms.
Like another plague?
Like another plague that could just wipe out any intelligent life. Now, these are barriers, and some people find them convincing, but at the same time, others think that maybe it's not enough to explain the absence of alien life.
Well, we also have to consider, what if the aliens choose not to come to Earth? What if they don't want to contact us?
That's a great question. I don't know. Would you decide to conquer the galaxy?
I mean, personally, if I had some free time on my hands, why not?
Yeah, sure.
If I'm trying to grow my civilization and we have the technology to advance, why not, spread to the galaxy and take advantage of the resources? But then that brings into the question, what are the types of civilizations that have the proper technology to do that? And that's where we get into the different types of civilizations that exist. There are three main types. Type 1 is a type of civilization that can harness the energy of the planet.
So only the energy that is located in the planet?
Exactly. So solar energy, harnessing the core's energy.
Okay.
Things we kind of do already. But
so we're almost a type 1?
I'd say we're, well, I wouldn't say it. It's shown that we are about a 0.74 type civilization. So almost there.
We're almost there.
We're working on it, but we still have a ways to go. Fossil fuels will get us so far, and then we'll get us so far, but eventually we'll need to fully maximize our use of the Earth's resources. Then we have a Type 2. Now, Type 2s are pretty cool. They take advantage of their sun. So they harness the entire sun. The power of this. Imagine that. It's the sun.
Think about how much energy that is.
From 8 light minutes away,
yeah.
It burns you. If you're pissing it off one day, it just burns you. But
these type 2 civilizations could harness.
Yeah, these type 2 civilizations can take this immense power using maybe some SPF 120 or maybe even 130 to harness this immense power of the sun and use that energy for their own, use.
Wow, that's a lot of energy.
That's a lot.
I want
of
to be
energy.
type 2. Can I join? Can I leave group, exit type?
Well, hold on, Abe. There's still a third type.
There's even more?
Yep. The third type of civilization, a type 3, is when a society can harness the power of the entire galaxy. Imagine being able to be at the center of the Milky Way galaxy and just harness all its power.
How would you go extinct after that?
Well, it doesn't seem possible. With such a diverse area of breadth of coverage, and with such a diverse population at that point, I can't imagine a possibility of going extinct. So that must mean there are no type 3s, right?
There shouldn't be, because where are they?
Well, we don't see them.
If they exist, then shouldn't we have seen them? But that also brings up the question of, imagine this type 3 did actually exist, and they were trying to reach immortality. What sort of stands in their way? And here I want to bring up the very famous or infamous second law of thermodynamics. And so the law states that in a closed system, the entropy tends to increase. And so what entropy is usually explained as disorder, but it has to do with how energy is spread out in a system, right? So, for example, here on Earth, when we're trying to use the energy of the sun is actually giving us very low entropy energy in the term as light, right? Mainly visible and ultraviolet light. And then this light is used up by plants and animals and life.
It's spread out.
Right, exactly. Then we use it, and then we radiate it back. Almost the same amount of energy that we get from the sun is radiated back into space. However, we radiate it as infrared. And infrared has more entropy than the visible and ultraviolet light. And therefore, the entropy has increased. And so that energy is no longer usable energy. And that's the key point. Energy is only good so long as it's usable. But the second law says that if you wait long enough, all the energy in the world will no longer be usable, and so immortality is never going to work.
I guess. If you're looking at it in that sense, immortality, can never work. But more on this type 3 civilization, do you think that if they had that much power, they would visit Earth, they would bother visiting? And if they did, who's to say they didn't visit it before we existed? Let's say they're so far advanced that they came by and passed some 50 million years ago, before we really were around to do anything. Maybe even before life was really on our planet, and decided this planet doesn't really mean anything. Well, we won't come back to it. And because of that, they decided never to come by and, visit.
No, that's interesting, because it reminds me of the theory of panspermia, which hypothesizes that life on Earth actually came from space. It didn't evolve on Earth. It actually came from somewhere else. So
we are all just stardust from the heavens.
You sound like Neil deGrasse Tyson.
Hey, he is a wise man.
So to continue with the type 3 and the civilizations, that's a good point. What if they don't want to visit? Like, what if they just conquered the whole galaxy and then they're like, we're done with this, let's move on? That's hard to imagine, though, because then I would assume that we would see some traces of a type 3 civilization, but
right.
We have not.
So we can, I guess, in this regard, for visible life, intelligent life, we can opt out the type 3.
Yeah, I would.
Now, what about type 2? Would they be able to communicate with us? Because they're still not so far advanced that we should be seeing them, but not so far back that they can't communicate with outside planets.
Well, so if we take the type 2 civilizations, with the amount of energy that they could harness. I mean, think about it. It only takes about 10 million years or 20 million years to conquer the galaxy.
Oh, only 20 million
Yeah,
years.
only 20 million years. Now, this might sound like
Easy.
a lot, but on the cosmic timescales of, say, the evolution of life, which is like 4 billion years on Earth, this is nothing. It's like a blink of an eye, right? 10 million years compared to a billion years is nothing. And so you would expect that even though they may be far away, or even though the galaxy may be too large, they would still conquer it in a blink of an eye.
You're saying for a Type 2 civilization?
For a Type 2, because with the energy they have, I mean, think about us. We're not even a Type 1, but we already sent probes outside of our solar system, right?
Huh. That's very
I
true.
wonder what a Type 2 would do.
What if a Type 2 civilization minds its own business? What if it's not like us and is wanting to explore but wants to just survive, wants to stay to its own devices and survive, and isn't naturally curious as we are?
That brings up a good point, because then we have no... why would we demand to see them, right? Why can't they just stay where they are, just living peacefully, harnessing the energy, and continuing on? But I'm not sure. Because then what if their energy just...
what if we become a source of their energy one day? What if our sun becomes their next target?
Right, exactly.
Dun, dun, dun.
Then it's Star Wars all over again.
It's
no longer
again. What do you mean again?
What? It already happened in a galaxy far, far away.
Anyway.
All right, so we talked about sort of the barriers of a civilization advancing and how a barrier could stop it.
What's another principle of the Fermi paradox?
So another possible candidate solution is the probability of life. And here's where it gets interesting. Because when we start talking about life evolving, well, okay, we have these 200 billion possibly habitable planets, right? To calculate the probability that life or intelligent life emerges, then you need to sort of multiply two numbers. One is the probability that only life would evolve on a certain planet, and then the other probability is that this life becomes intelligent. And so to calculate the total probability, just multiply the two together, voila, you got your answer. That sounds easy. Not really, because the biggest problem with this is trying to estimate what the probability of life is.
I was going to say, you can quantify the probability of life?
We only have one data sample.
I mean,
that's us.
I've seen some pretty, small studies with a group of 5. Isn't one just as good?
Yeah, it's enough to build the whole statistics.
Yeah, just one.
Yeah.
That's about as valid as the anti-vaccine study. Anyway.
Back on topic. So yeah, you take these probabilities, you multiply them together, and you get your answer. It sounds simple. It's not really. And have you heard of the Drake equation?
Yeah, I hear he's quite the physicist among his other talents, including rapping.
So Drake, that Drake.
I didn't forget about Drake.
Yeah, he came up with this equation that sort of tells you the probability of detecting sort of radio waves coming from aliens, but it's mainly the same principles as the probability of finding life out there. And one of the criticisms is that, like, yo, Drake, where'd you get all these numbers from, right? Well, how do you know what the probability of life emerging is? So it's really hard to take this probability of life solution seriously if there is no way to estimate how many, what's the probability of life evolving on a planet, right?
Well, if the planet is based or named after Gloria Gaynor, then we know for a fact that it will survive, right?
Yeah, the probability is 1 then.
Of course.
Yeah,
1 1 1.
So it's interesting because Carl Sagan, I think, had a response to this. He was saying, okay, assume the probability of life is really tiny, okay? But we still have these 200 billion planets. And so no matter how small the probability of life is, we should still expect something, whatever it is, something, just because of how vast the cosmos are. And then Fermi sort of toppled this reasoning, and he said, well, no, flip it around, right? We don't see any alien civilizations, therefore the probability of life is really small. And this is sort of part of the paradox.
So if life could exist, what are the odds? And if those odds are very slim, there still should be, even if it's 0.0000001% out of 200 billion opportunities, there are still a couple chances in there.
Exactly. That's what Sagan was arguing for.
So with those couple of chances, why haven't they advanced? Or have they not had the opportunity to advance? Are we so far ahead of the curve that we're beating the other, basically beating the others?
Exactly. That brings us to the third possible solution, which is that life on Earth has developed very early on. In a cosmic timescale, that is.
So we're ahead of the curve. We showed up early to this party. We're
exactly.
the lame.
We're the first people there. We're not Arabs. We're late. So that.
Wait. Are you saying that the universe doesn't run on Arab time, or the rest of the universe does, and we just so happen to be on time?
Yeah, we happen to be on time, because if you think about it, then life has evolved pretty early on in cosmic timescales, and so we don't have any reason to expect that other life has already evolved and reached this sort of advancement where they could colonize the galaxy. So this might be a solution, and it's getting popular, I believe. But what do you think? Do you think that this could solve it? That we're just early, we don't see anyone?
That seems pretty convenient, saying, "Oh, hey, we just got here before everyone else. That's why no one's here." That's like that guy who threw a party and no one showed up. Yeah, I'm just the first one here. Sounds kind of sad. Maybe no one else is coming.
That might be a possibility.
Have you ever heard of a von Neumann machine, Abe?
I have, but I might need a refresher because I have forgotten what those are.
Von Neumann machines are a really cool concept. It's the idea that a planet doesn't have to evolve to a Type 2 or Type 3 so long as it has these small robots that can harness energy or power, by taking resources from a planet and self-replicate. Now that is the key.
Robots that self-replicate.
Robots that can self-replicate, build miniature versions of themselves inside of themselves.
That's genius. No wonder von Neumann was such a genius.
So von Neumann came up with this idea for a machine, and thusly called it the von Neumann machine. What a guy. And it's the idea that you could create one of these devices that would go explore the universe and harness the power of planets and constantly self-replicate and not need to have humans. It's not limited by our barriers, disease, by politics. Its single purpose is to harness this energy and self-replicate. So a society, helping with these machines could very much, at a Type 1 or Type 2 or in between phase, send out one and have them kind of, I wouldn't want to say take over, but consume the rest of the surrounding planets and using them for resources and then kind of bringing that back to their planet. So that's a possible
mechanism of conquering a galaxy, perhaps?
Right, that kind of it kind of gets past the Type 1, Type 2, Type 3 barrier. Mm-hmm. But this is stating that we could build such a machine that honestly seems possible with the technology that we have, how it's advancing, but is still far from being possible. How do you prevent a machine like this from attacking your own planet, from harnessing your own planet's resources, or how do you control it, especially if it's outside the range of a remote or any sort of device that could control them?
Exactly.
How do you know you can bring them back? So that was just a possible solution or a possible theory that could work. And John Newman has talked on the topic of the Fermi paradox, and so I figured I'd bring him up.
Did he detail the von Neumann machines and how they work, or did he just propose sort of a theoretical idea that could maybe work, like leave it to the engineers to do it.
It was sort of a general idea, but then he brought up a device that was talked about in the past called a Dyson sphere.
Ooh, Dyson spheres.
Did I say the key word,
That's
Abe?
the key word for this episode. By the way, I'd like to remind our viewers that if they have any thoughts and ideas, comments about the Fermi paradox, then
We'll be doing a Q&A session in 10 minutes. That's right, at 6:10 p.m. We'll be taking a quick intermission and coming back for a
Q&A
awesome Q
thing,
session. Yep. So get your questions ready. We have our phones present. We're unblocking you currently.
Yeah.
We're looking forward to your input.
Back on topic of Dyson spheres.
Dyson spheres.
By the way, Dyson,
Not the fan.
not the fan. Freeman Dyson actually never got his PhD. Yet, yeah, he never got his PhD. Yet, he's one of the most brilliant physicists of the 20th century.
I guess
Makes you think.
I guess getting a PhD is no longer a barrier of entry for that.
So he came up with this idea of the Dyson sphere, which is sort of these. It's similar to von Neumann's idea, but it's more on the energy side than the replication side.
How so?
Dyson spheres. The purpose of Dyson spheres are to harness the energy of some sort of source. So, for example, you can have a sun, and then the Dyson sphere would surround the sun, absorb all its energy, and perhaps store it. And then for later use, you could utilize these Dyson spheres.
Oh, that sounds like a huge project right there.
What if I want to research that?
What do you mean?
Because then, if I could figure out how to build a Dyson sphere, I'd be making the money.
I don't know if money is what you'd be making, but enemies definitely. Now, Abe, bring us back to this Fermi paradox. Tell us how it ends.
I hope it has an end, but it doesn't seem to for now. The possible solutions, well, we talked about three main ones that people usually talk about, and none of them seem very satisfying in a sense, because
None of them give us an answer that we want.
well, exactly, and it's just so hard to pinpoint exactly what's going on, right? To me, what I think is going on is probably that life is just very improbable, like extremely improbable, coupled with the idea that life on Earth evolved early on. And so if you take those two together, I think that might give an adequate explanation. The problem is I have no evidence for it.
I honestly think it is a combination of those things, but also taking into account that there is a large barrier that we have passed as a civilization that many others might not have. The barrier to become an intelligent life is a big one. It's a big step to go from just doing what natural evolution has taught you to being able to think, cognitively think, use your own frontal lobe to think. And that brings into the idea, what is the next barrier that we have to overcome? And I think when it comes to that, cliffhanger. We'll see you on the next episode of. So I think when it comes to that,
Do you think it's mainly political in a way, or?
I think it's a barrier that is technological. So I feel
Okay.
like we are reaching a
limit in technology?
I believe
An
so.
asymptote?
An asymptote in technology that's kind of going to limit where we can progress. Eventually, processors are only going to get so efficient. We're not going to be able
Moore's
to.
law.
Right.
Yeah.
And so, at what point do we have to look into new technologies to reach this next barrier? And that's kind of my thought process is no society, no alien life has gotten past that point. If not the one before us, this upcoming one is so difficult to overcome. Because
That just no civilization.
right, each barrier before and the next, just alone to be habitable is a barrier, and to overcome that one is a difficult one. And let's say 10% of those go on. Then beyond that is to have life, 10%. Beyond that, to a develop life for over, millions and billions of years. And again, each one of these is dividing the odds.
Right, making it shrinking.
Right, and each barrier becomes even more difficult in itself. So not only are the odds getting smaller, the number that are passing from one to the next, the percentage decreases.
Exactly, because you have to multiply independent probabilities, and then the number just keeps going down. So you're more on the barrier side of the solutions, as opposed to, say, the probability of life, the probability of life does factor into your assessment, but perhaps not the idea that we developed early on, right?
Mm-hmm. So then we get back to the idea, what makes us intelligent, Abe? Besides the piece of paper that says I graduated.
That's a great question. I'm not sure if I have the right answer to this question, but I believe it's very hard to say when exactly humans became intelligent in the film of evolution, right? A lot of people link it to language, which is it's an idea, and it has some merit because
then you can communicate with your fellow species, and
exactly,
it's no longer one person; it's many that
right,
think collectively.
Right, exactly. And so it might be a language, like the development of language. It might be the interplay between sort of language, but also the brain connections that have developed. So it doesn't necessarily mean brain volume, but it could be brain density or some sort.
So you're thinking the concentration of neurons in different parts of the brain, like the frontal lobe. I think we have one of the highest concentrations of neurons. So not just size of the brain, but concentration of neurons within that lobe compared to any other, animal.
Yeah, because lots of animals have larger brains than us.
Yeah, like look at an elephant. Look at a blue whale. Those things are
huge.
Like at least the size of a sedan.
Oh yeah.
Probably bigger.
No, it's smaller.
Smaller than a sedan?
Yeah, it's nothing.
Yeah.
Yeah.
I think blue whale's brain is the size of a sedan. The brain alone.
The brain alone.
So it's not about the physical size, but the density. And so you look at animals like dolphins and like octopi.
Mm-hmm.
The squids have such a high level of intelligence because they have a high concentration of neurons in their brain. It's really a cool concept. You should see the interactions between a squid and a jar. Like that alone.
And how they open.
It can open up the jar and get out. Yeah, it's a quite intelligent species, and that goes to show that maybe it's just getting this higher density of neurons over time, and that's what will advance our intelligence and, by association, our technology. But again, that brings the question up: is the barrier to technology synonymous with the barrier to intelligence?
I'm not sure. That's a great question. The thing about developing intelligent life is that you have to start from somewhere as well, and so you have to concentrate on the stages of evolution.
Well, that's why I'm at Wayne State. I want to start somewhere.
You gotta aim higher and be warrior strong.
Yep, get that education.
And then, so I think usually they're dissected into maybe 5 stages or more of evolution. Like, first of all, you need the evolution of the primordial life, which can self-replicate, and that might not be a trivial thing, right? But at the same time, assuming that it's not, or it is trivial in a way, what about the other stages? What about developing multicellular life? Maybe that's the key to intelligent life, because as we know that as soon as multicellular life developed, then there was sort of a rapid expansion or a rapid acceleration in evolution afterwards. So
I think it was after that point our species evolved exponentially because we could actually pass on genetic code at such a fast rate.
Right, exactly. And so it's hard to pinpoint where the hardest part of evolution would be, but some people are arguing that it's the transition from single cellular life to multicellular life. And then after that, the evolution just kicks into high gear or something.
Well,
Oh.
it's reached time for our intermission, so prepare your questions. Ask us. Let us know. Do you think you're intelligent? Show off to us. And hit us with any questions you might have about the Fermi paradox, intelligence itself, evolution,
Nobel Prizes.
Nobel Prizes, rock climbing. Heck, I'd love to answer some questions about rock climbing. So we'll be back in around 7 minutes. We look forward to seeing you all with our ears. ladies and gentlemen. So, that was some lovely music, Abe. Wouldn't you agree?
That was great. That was.
I wonder if they have that on vinyl or record. Speaking of record, have you heard about the Voyager's Golden Record? It's its hottest, latest album.
Tell me more.
Well, the Voyager's Golden Record answers one of our listeners' question. Diana Forbes asks,
how much of the universe have we surveyed?
And that brings me to the topic of what have we really done to survey our universe? One of these attempts to kind of describe what humanity is this Voyager Golden Record. Now, let me explain this properly. In 1977, we sent out this kind of gold record-shaped plating that has on it the dimensions of what we consider to be important as a human race, what would kind of define us, basic principles of physics that, when decoded, are able to kind of give them information about us using the principles of physics that should be applied no matter where they are, no matter where.
So these are universal things that pretty much any civilization could decipher and then understand that we are intelligent.
Right, using those basic laws of physics that apply everywhere to kind of translate these messages that we sent. Like one of them is
give me some examples.
One of them is like a radio wave or a wave that kind of. Well, Abe, are you familiar with this?
I have seen it before, and I've seen there's some sort of carving on it or drawing that is supposed to symbolize the hydrogen atom, but I'm not exactly sure if I'm remembering correctly. It's like a gold plate, like you were saying.
Yeah, it has this like signal that's supposed to be represented by being etched, and it's a series of vertical lines similar to like a television, where there's a picture of 1, 2, and 3 lines all kind of in succession that are to note binary numbers, and the duration, kind of the length of each one, is the duration of these waves, and it's complex. Like, I don't quite understand most of what's written on here, but it looks absolutely beautiful. And if you haven't bought the latest album, you got to check it out. They've got some great hits on there. So
I want to tackle that question from a different angle.
Diana's question?
Yeah. So just a reminder, the question was, how much of the universe have we surveyed? And to answer that question on the largest scales, then I have to bring up the cosmic microwave background.
Oh, and you have to. You just brought up one of my favorite topics, Abe.
So the cosmic microwave background is, simply put, the baby picture of the universe. It's literally that. So there were these two physicists, Penzias and Wilson, and they were setting up this radio antenna, and they were pointing it in all different directions, and they found that the signal was pretty much the same, no matter which direction they pointed it at.
So kind of like a static noise.
Exactly. So when you turn on your TV, you have, and it's not, connected to any station or something, then you have all the static on the TV. About, I believe, 1% of it, maybe less, I forgot the exact number, but about 1% of it comes from the cosmic microwave background, which is the radiation that was left off from the Big Bang.
So you're talking about that white and black, really loud, blurry noise that comes on the TV when you go to a weird channel.
Exactly.
Huh. I always thought that was the program where there was really angry zebras fighting with each other.
That's on Channel 2, though.
Oh, I see. Animal Planet.
Right. And so we were able to sort of survey the sky and look for the signal, and we found that this signal was actually the afterglow of the Big Bang itself. So about 400,000 years after the Big Bang, because the universe was opaque before that. Light could not penetrate all the atoms, and well, there were no atoms back then, but all this, the particles there, light could not penetrate it, and so the universe was opaque. And then after 400,000 years after the Big Bang, light could actually finally escape. and then what we're detecting is that light after the Big Bang. So we have this picture, this baby picture of the universe.
Oh.
Yeah, it's cute. And what we discovered is pretty remarkable. It's that the universe is remarkably smooth, and that means that the temperature differences from one place to another are not that much. They're actually extremely tiny, which has forced physicists to sort of try to tackle this problem. Like, the universe is huge, but yet it seems to have interacted with itself a long time ago. And how did that happen? And that was sort of one of the problems of cosmology. It still is a problem, but it does have some proposed solutions. So to answer the question, we have surveyed quite a lot and not enough at the same time.
What do we do to survey? How do we go about? What are we doing to receive messages and kind of send out messages?
A lot of the detection happens with telescopes, mainly. For example, the James Webb Telescope is planned to go up to space, and it's supposed to be a radio telescope, which would allow astronomers to intercept a lot of radio signals that otherwise could not be possible using visible light or, say, ultraviolet.
And isn't being interfered by the atmosphere of the Earth?
Right, so they shoot it up into space so that they could get a much clearer picture of what's going on.
That's really cool.
It is.
When does this go up?
I'm not exactly sure. We could check it. But there's also other types of telescopes, like the Hubble Deep Space Telescope, that has a lot of beautiful pictures.
It does.
See, we also just have telescopes that are here on Earth. So take Hawaii or Chile, because they have the right atmosphere and high mountains for pretty good observation.
Mm-hmm.
And so those telescopes are used to survey the sky, to pinpoint certain planets, stars, locations, all that stuff.
So this is visible, what we're trying to do to see the universe. What about on a smaller scale, using frequencies, using microwaves, radio waves? We have these waves that, we should be able to shoot out. Are we using those in any way?
We do use the same principle. So we intercept the light, and we get a picture of the cosmos out there. At the same time, if we want to probe the smallest scales, then we're going to use the same principles by shining light on these objects with ever increasing frequencies.
So like a really, really big flashlight.
But with very high frequencies as well. What's remarkable is that there's this thing called the electron microscope. And what it does, it uses actual electrons to image things instead of light. And how does this work? Well, electrons are we usually think of electrons as sort of particles, right? An electron is here. It's like a tiny baseball. I could throw it, and I could, all that stuff with particles. It turns out that nature does not behave that way. Electrons have a wave nature to them, meaning we can associate a wavelength to them. So kind of like light, which is an electromagnetic wave. It has a wavelength. Electrons could be associated with a wavelength. And it turns out that the wavelength of electrons is pretty small, which is great for imaging. And so we use these electron microscopes to have very, very clear images of very tiny things.
So let's take a look at one other question one of our users gave. They're asking, if there is no free will, how does the Fermi paradox apply? So this is kind of funny. It's a callback to our last episode. We discussed the possibility of free will. Is it real? Does it exist? And to answer your question, it doesn't. Moving on.
Taking a question from Zainab, who's asking, what is life?
Wow, that's a broad question. Well, a great man once said, life, if nothing else, is synonymous to love. And if we go by that, we're basically asking, what is love? And everyone knows, when asking the question, what is love, there's only one answer. Abe, do you know it?
Baby, don't hurt me.
Don't hurt me.
No more.
So, thank you, Zainab. Thank you, Diana. Thank you, everybody, for your questions. Thank you for tuning in this week to From Atoms to Axons with
Ibrahim Shahrur
and Bilal Hamoud. We look forward to seeing you next week. Have a wonderful evening.